So in this example, we're going to look at the P series, which is a very important series, and we're going to see lots of places where it crops up, but we'd like to know when it converges. So this is one of those standard series you should have in your back pocket. Geometric series, which you talked about in the last lecture, those series you should have in your back pocket, ready to pull out at any time and use them, know the sum of them, know convergence conditions for geometric series, the R value being smaller than 1. P series are another series that you should have in your back pocket, ready to pull out at any time and use. And in order to use them, you need to know when they converge. And that's entirely dependent on what the P value is. And that's what this question is about. It's about trying to figure out, when do P series converge? What are the values of P for which you get convergence? And I'm going to make the claim, which will verify, that the series 1 over n to the p, n equals 1 to infinity, converges if and only if p is bigger than 1. So only when p is big enough do you get convergence. In some sense, you want p to be big enough so that the denominator gets big fast, so that the reciprocal gets small fast, so that the tail end of the series is really small and not contributing much to the sum, in which case you get convergence. Because this whole idea of convergence is really about how fast do the terms go to 0. The harmonic series is an example of one. So when p is 0, or sorry, when p is 1, that's our harmonic series. The terms go to 0 in that series, but they don't go to 0 fast enough apparently, because we've already shown just a couple of examples ago that the harmonic series diverges. So the question really is, a series converges if the terms go to 0 fast enough. What do we mean by fast enough? Well, if they go to 0 fast enough so that the integral converges, then the series converges. That's what we're doing today. In later lectures, you'll see other conditions by what we mean by go to 0 fast enough. And in this case, to go to 0 fast enough for the P series means that P better be bigger than 1 to guarantee that denominator is getting big enough so that the reciprocal is getting small enough and going to 0 fast enough so that the terms converge. So let's figure out how to get these results. So one of them we can knock off immediately. If the series is going to have any chance of converging, the terms better go to 0. So if the terms don't go to 0, then we know it diverges. That's the test for divergence that you saw last day. So let's just look at that case. If P is smaller than 0, then it really means that what looks like a term on the denominator is really a term on the numerator. Because if P is negative, then we can always write the series where the exponent is now positive. Right? If P was negative, then I'm just going to write the expression as I normally would, n to the power of that positive value of P. And does this series converge? Well, no, it can't possibly converge because the terms don't even go to 0. As n gets bigger, the terms are getting bigger. So this diverges since terms don't go to 0. Okay, so that one we were able to dispose of rather quickly. Now let's look at the other cases where a little bit more work is involved. I could also include P equal to 0, because if P is equal to 0, then all the terms are just 1, and again the terms don't go to 0. If P is 0, then this is just a series of 1 plus 1 plus 1 plus 1 plus 1 plus 1, and the terms aren't going to 0, so it diverges. So what about if P is between 0 and 1? Then what we'll do is we'll apply the integral test. We'll apply the integral test. What are the conditions? We need continuous, so the function here is 1 over x to the p. That's continuous. It's decreasing, and they're all positive, so we got those. We've satisfied the hypotheses for the integral tests. So then we can look at the integral. The integral from 1 to infinity of 1 over x to the p dx. If this converges, then our series converges, and if it diverges, our series diverges. So what is our integral? Well, I'll switch to a limit for dealing with that upper limit of integration. And what is our derivative here, this would be x to the 1 minus p over 1 minus p from 1 to infinity. And I will just rewrite this as 1 over 1 minus p. Actually, let's leave it like that because this is in a nice form to figure out what we've got. As m goes to infinity, something's double writing here. As m goes to infinity, 1 over 1 minus p m, that should be an m up there, m to the 1 minus p minus 1. And what happens as m goes to infinity? Well, if p is smaller than 1 but bigger than 0, then 1 minus p is a positive number. So this is m to some positive exponent. And m's getting big. So a big number to a positive exponent is still big. So this thing's going to infinity. M to the 1 minus p, that's going to infinity. So this part is heading to infinity. And so the result is that this diverges. And so the integral diverges, therefore the corresponding series has to diverge. So by the integral test, the series 1 over x to the p from n 1 over n to the p n from 1 to infinity diverges if p is between 0 and 1. Okay, what about if p is exactly equal to 1? Well, our previous argument doesn't work when p is exactly equal to 1, because here the antiderivative of 1 over x to the p, well, that was given by another power of x. But that's not true when we're taking the antiderivative of 1 over x. The antiderivative of 1 over x has a different form. So that's why it deserves its own special case. The antiderivative of 1 over x is the logarithm of x. And I'm just going to write its logarithm of absolute value of x, but I'm just going to write log of x because we're over an interval consisting of positive values. So that's from 1 to infinity. And again, evaluating the logarithm at the endpoints, well, as x goes to infinity, the logarithm goes to infinity, so this diverges, this is infinite, so it diverges. So the integral diverges, therefore, by the integral test, again, the series diverges. Of course, this was exactly the argument we gave on the previous page, because again, this was just the harmonic series that we're dealing with. So I could have referred to that and said we already did this case, but I wanted to present this full argument in all its details. So in this case, we just dealt with p equals 1. Notice that the integral gave us the logarithm, and therefore we got divergence of the series. Okay, so there's one last case we need to deal with, and that is when p is bigger than 1. And by our claim above, we apparently believe that this is where all the work is involved in getting convergence, because that's where we're saying convergence happens. So if p is bigger than 1, then what is our integral? Well, this is 1 over x to the p dx, and our integral in this case, limit as m goes to infinity, of 1 over 1 minus p, 1 over x to the p minus 1, and that's from 1 to m. So there's our antiderivative, and as m goes to infinity, m comes down, it's in the denominator, that's going to go to 0, so what's left is just a 1 over p minus 1. I've written p minus 1 because it's really going to be negative, because this is the lower limit of integration when you plug in. That'll be negative, so I've just swapped the placement of 1 and p on the bottom to take care of the fact that there was a negative sign in front. So the integral converges. And so if the integral converges, then by the integral test, the series converges too. And so there's the end of our result. We've proved our claim. We had divergence in all the other cases except when p was bigger than 1, and we got divergence in all those other cases by doing different arguments. One was terms don't go to 0. That was when p was smaller than 0. One of them is an integral that involved power of x. In the case when p was equal to 1, the integral involved a logarithm, but all of those were separate arguments to come up with divergence. But finally, when p was bigger than 1, apparently the denominator is small enough. Apparently the denominator does grow fast enough so that the reciprocal does go to 0 fast enough that the terms of the partial sums go or converge.